Hi, my name is Sohn, like she said. I'm a senior here at Tahoe Expedition Academy, and I chose to do my capstone on the aerodynamic heating for sounding rockets, and specifically the prediction of aerodynamic heating for sounding rockets. Right. First of all, what is aerodynamic heating? It's probably a fairly new term to most of you, if I had to guess. But aerodynamic heating is a phenomenon where you're moving very quickly through the air, and as such, the air is sliding along and heating up any exposed surfaces, which to hundreds, sometimes thousands of degrees. This is a problem because materials often reduce in strength over temperature. If you ever had like a plastic Tupperware you left in your car and now it's all bendy, same idea. And when you go really fast and strip all the paint off, your drag increases, which reduces your overall performance. That video was a lug cam from a sounding rocket where you could see all of the paint coming off and then more and more damage happening to the rocket until it finally broke up. This, as an example, this is one of the missions that I looked at during my studying in industry. I'm going to call it STORT. If you want to try and pronounce the German, you're welcome to, but it roughly translates to key technologies for high energetic return flights of reusable stages, which is sort of the thing around like Falcon 9 or SpaceX, that sort of thing is what they're doing science for. This was a 3-stage sounding rocket that was launched from Andøya Space on the northern tip of Norway. It reached, and during its flight, it reached Mach 8, or around 5,600 miles an hour at 35 kilometers, and it stayed there for around 70 seconds. During this flight, the very tip of the nose got up to over 1,000 degrees Kelvin, or 700 degrees Celsius, which is around 5 or twice the temperature that aluminum starts reducing in strength and effectively melting at, which means that if this had been made of aluminum, it would have completely melted and broke up long before it even got here. For my scales at the amateur level, we're only going maybe Mach 3 or 4, or 3 or 4 times the speed of sound, so only 3,500 miles an hour. But our technologies and materials are much lower temperature, so they start melting a lot earlier, which means that our drag starts to increase as the surface roughness increases and everything starts flaking away. But why this topic for me specifically? I've been interested in rockets and spaceflight from a young age. I think there's pictures of me launching rockets with my grandfather from like age 8 or something. I couldn't find those pictures, otherwise they'd be up here, but they exist. And through those years, I've wanted to fly rockets even higher and faster than I have before. I've personally flown up to 49,200 feet with this rocket here named Relapse. There was a booster stage on it, but it got lost in the desert. And I've flown group projects up to 60,000 feet with this orange rocket over here. And outside of my own space, this is a pretty often asked question in the rocketry community of, my rocket is going to go this fast, is everything going to melt, or is this not even something I have to worry about? With my 449,000 foot flight, I set the amateur record for high schooler, as far as I know, worldwide. And then I've also been the T-Rocketry Club founder and lead for 3 years. However, in order to start off this project, I needed a real-world problem statement that applied to just people other than just me. So I came up with the mathematical models for determining aerodynamic heating effects at high supersonic speeds are inaccessible to the amateur rocketry community. This led me to my essential questions for this project, which were, when is aerothermal heating a non-trivial issue for amateur sounding rockets, and what can we do to mitigate the effects of this aerodynamic heating? Some of the project goals that I had coming into this project were just to learn more about air heating from a physics and first principles perspective, figure out which phenomenons attribute to it and then subtract from it, and then conduct research into how this has been calculated and protected against in the past by real industry experts. And then the biggest part was to create a tool to predict this heating for our amateur flights, and then compare those predictions to observed heating in my own flights as well as in flights from literature. Speaking of literature, 4 papers that I took a lot of inspiration from for this project were this first one by, I believe, a Brazilian group, which went over a basic idea of prediction of aerodynamic heating. This one by NASA, which goes over the way that NASA has done thermal protection or protection against aerodynamic heating over time since like the space shuttle era. And then there's another one by NASA, which gives an idea of like the basic overviews in physics physics phenomenon that contribute to it. And then this last one was the paper for STORT that I drew a lot of the very high end of this information from. For my fieldwork, I spent 4 days in LA and met with 4 experts, 2 in person, 2 online, as well as did a test flight for this rocket before bringing it up to Alaska to fly. These were the experts that I met with. Alexander Patras was an industry expert, and he helped me gain an understanding of the ways that aerodynamic heating is predicted in industry, which is primarily very large-scale fluid dynamics simulations that require immense amounts of computing power and are very difficult to set up. I also met with Bobby Rogers, who was the aerodynamic heating analysis lead for the USC rocket team, still the only rocket team to go to space somehow. And he gave me more of an insight into how they do it, which is a much simpler empirical design that was sort of what I'm looking to do. Andy Garrick also helped me with figuring out what exactly I needed for that empirical design program, because he has spent several decades at McDonnell Douglas, I think, and kind of knew in the heat transfer department, so he knew sort of exactly what I was looking for. And then Julian Donat has a master's in supersonic aerodynamics and has done a lot of this analysis before for both class and for personal stuff, and he was invaluable for a lot of the specifics on stuff, on programming mostly. After meeting with all those experts, I went out to the Mojave Desert and did a test launch to around 12,500 feet in order to test our structures and electronics and recovery systems, as well as just to test our operations, like how we moved around and conducted the launch. And I'm happy to say that it went perfect, as you can probably guess. And we recovered it in perfect condition, making it ready for a 60,000 foot flight in Alaska. Specifically from this field work, I learned a lot about the industry versus amateur levels of heating prediction, as well as the ways that the different groups handle it. As well as I learned a lot about driving in LA, which if you've ever been there is an experience. So that was definitely one of the harder parts of this trip, was navigating LA without, and we of course proved that the rocket was ready for flight. Without further ado, this was that flight that I was talking about. So we picked Alaska primarily because a couple of my friends said something to the effect of, yo, it'd be really cool if we launched a rocket in Alaska. And then too many other of my friends said, yeah, let's do it. And then 6 months later, here we are. So it's also, the launch site up there is also just great because it's a like 3 mile or 4 mile diameter frozen lake bed. And if you land anywhere on it, it's really easy to get to if you land on it, because you can get there with a snowmobile. These are the 2 rockets packaged up in their crates, ready to be handed over to TSA, which shockingly didn't care that much. Take from that what you will. The entire group was a 5-person team, including myself, and we launched out of Lake Louise, which is around 3.5 hours northeast of Anchorage. And then on this team, I was primarily coordinated all the different people, figuring out who needed to make what, and then how they all needed to get to the one spot in order to go to Alaska. On this flight, we got around 60,000 feet of altitude, or just under 11 or 12 miles. We got just under 3 times the speed of sound, or Mach 2.9, and we successfully recovered all of the parts. This is the onboard footage from the from the rocket. And just there was the second stage burning out, so it's just on its way to apogee now. And then over here is the rocket lifting off, which I really wish you could see better, but oh well. Yeah. This was it as we found it. Here's us pulling it from the snow. All we could see was the little cord coming out, sticking out of the snow. And we had to rip the rest of it from the snow, which was fun. And we recovered it around 3.5 miles from the launch pad, but I mentioned the lake is around 2.5 miles wide. So we did around 0.6 miles. That math doesn't quite add up, but you know what I mean. Around 0.6 miles of just post-holing through the snow in order to find this thing. And unfortunately, my temperature sensors didn't work, so I didn't get like a curve, but this part on the camera shroud started to melt, so we can figure out that it at least got to the temperature where this polymer starts to melt, which is PEKK. It's a polymer name I can't pronounce, but it melts at around 160 degrees Celsius, so we know that it got at least that hot during this flight. For my final product, of course, I said I wanted to do a computer program in order to predict this aerodynamic heating. I've worked a good bit on this, but it's not quite ready yet. It's written in Jupyter Notebook and Python, and it uses the second order shock expansion and compressible heating theories that I learned from my experts and from the literature. The idea is you can input like a rocket shape, so you just put in the shape of the rocket, and then it will output how hot it will get over time, so that you can use that information to both figure out what materials you're going to need, as well as if you need like sacrificial materials and how much of those that you do need. I'm working towards around 10% agreement with the other methods that I've found, that like say the supercomputer or that sort of thing. And because that's around the limit of what we can get out of our flight simulation software. So any more accurate than that is like, you're accurate to this profile, but that profile isn't that accurate, so it doesn't really make sense to get any better than that. And I'm planning to make it fully open source on GitHub. My conclusions for this project were that aerodynamic heating was not an issue below around 2.5 times the speed of sound, but above this, it can become a problem depending on how fast and what altitude you're going to. And that analytical methods or just mathematical methods are perfectly suitable for predicting flights or predicting heating for amateur flights. This led me to my essential answer, which was, according to literature and field experts, aerodynamic heating is not an issue below Mach 2.5, but becomes a problem as speed increases. This heating can be mitigated by using either higher temperature materials like metal instead of plastic, or sacrificial layers that slough off and carry some heat away with it, with your decisions made by numerical analysis. As for some of my future endeavors, I'm planning to shoot for over 100,000 feet before the end of the school year, as well as get better data from that flight with actual temp data and better camera footage as well. We'll see if any of that happens. Any questions?